Factorising quadratics of the form ax² plus bx plus c, not equal to 1. This factorization involves an extra step compared to the previous one. You have to find another combination of numbers that gives the coefficient in addition to the two combinations used in the previous lesson. In this way, we have to find other two numbers p and q, which must meet the condition n the following shown on screen. Giving that the general form of a quadratic expression is shown in the following on screen. Then, if we are sure that one of the numbers between p and q is 1, or -1, the expression must be written in the form shown in the following on screen. Or we have the following shown on screen. In this way, the following two conditions must meet simultaneously. We have the following shown on screen. We also obtain the following shown on screen. Or hence, we now have three conditions, one for each coefficient, constant. We obtain the following shown on screen. For example, if we are asked to factorize the quadratic expression, we obtain the following shown on screen. First, we have to point out the coefficients and constant. Here we have a equals 3, b equals 7 and c equals 2. Then we try to find the other numbers, p, q, m, and n. From the third condition we have the following shown on screen. Hence, we have four possible combinations for m and n. M equals 2, n equals 1, m equals 1, n equals 2, m equals -1, n equals -2, m equals -2, n equals -1. Likewise, for p and q, we have four possible combinations as well, given the first condition. They are p equals 1, q equals 3, p equals 3, q equals 1, p equals -1, q equals -3, p equals -3, q equals -1. However, this is not important, as we always have them multiplied together and the result is always the same. Now, we have to look at the second condition. We have the following shown on screen. Thus, from all combinations for m and n, only m equals -1 and n equals -2 are suitable. We have the following shown on screen. Therefore, the original quadratic expression is factorized as the following shown on screen. Example 1. Factorize the following quadratics. A. 2x² minus 5x plus 2. B. 4x² plus 9x plus 2. Solution 1. A. We have a equals 2, b equals -5, c equals 2. In addition, we have the following combinations shown on screen. Likewise, we have the following shown on screen. Therefore, we have n equals 2 and m equals 1. Hence, the factorized form of the quadratic expression 2x² minus 5x plus 2 is shown in the following on screen. Or we obtain the following shown on screen. When expanded, this expression gives the following shown on screen, which is identical to the original expression. B. We have a equals 4, b equals 9, c equals 2. In addition, we have the following combinations shown in the following on screen. Likewise, we have the following shown on screen. Thus, n equals -2 and m equals -1. Moreover, since p and q are usually different, we have p equals 4 and q equals 1. Hence, the factorized form of the quadratic expression 4x² plus 9x plus 2 is shown in the following on screen. Or we obtain the following shown on screen. Let's prove this by expanding the last expression to confirm the result obtained. Thus, we have the following shown on screen, which is identical to the original expression. So far, one of numbers p and q was always 1. But, what happens if both p and q are different from 1? Let's consider the following quadratic expression shown in the following on screen, where a equals 6, b equals -11 and c equals -10. Starting from the constant c, we obtain the following shown on screen. There are 8 possible combinations that give this result: m equals -1, n equals 10, m equals 1, n equals -10, m equals -2, n equals 5, m equals 2, n equals -5, m equals -5, n equals 2, m equals 5, n equals -2, m equals -10, n equals 1 and m equals 10, n equals -1. We must find the suitable combination. We have the following shown on screen. Thus we have the following shown on screen. Or we obtain the following shown on screen. None of the combinations can be used here. Therefore, we must look for another way to express the given quadratics. We must try to write it in the form shown in the following on screen, where both p and q are different from 1. Now, let's discover the relationship between p, q, m, and n. Expanding the expression, we obtain the following shown on screen. Therefore, we obtain the new expression for the coefficient b. We have the following shown on screen. Substituting the value of b, in our example, we have the following shown on screen. Or we obtain the following shown on screen. From all combinations that give p, q equals 6, given that mn equals -10, we choose n equals 5, m equals -2, p equals 3 and q equals 2, we have the following shown on screen. Therefore, the original expression is factorized as the following shown on screen. Proof: expanding the last expression, gives the following shown on screen, which is identical to the original expression. It is clear that this method is more inclusive. We only use the first method when we are sure that either p or q are equal to 1, otherwise, we use the second method for finding all coefficients required. Example 2. Factorize the expression shown in the following on screen. Solution 2. We have a equals 8, b equals -10 and c equals 3. Most probably, p and n are different from 1 as there are 4 other possible combinations, 4 and 2, 2 and 4 and their negative counterparts. Hence, we are not going to take the risk of using the first method, as we may find ourselves blocked on the way. Hence, we aim to write the expression in the form shown in the following on screen. We have the following shown on screen. So, m may be one of the following numbers, -3, -1, 1, and 3, as well as n, m, and n, must have the same sign to give 3 when multiplied. In addition, we have pq equals 8, and we have the following shown on screen. The only combination possible is the one that produces the arithmetic expression shown in the following on screen. because the value of this expression is 10. Thus, based on this description, we have n equals 3, m equals 1, p equals 2 and q equals 4. Therefore, the expression becomes the following as shown on screen. We have the following proof shown on screen, which is identical to the original expression. That is all for lesson 6.4.4, and the end of tutorial 6.4. To continue this chapter, please watch 6.5, Introduction to Algebraic Fractions. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.